Okay. So what we are trying to do now is Hamming code, and Hamming code, in fact, is for error correction. So what we would see an example. It's a very interesting example, I would say, and we would do it with you. Um, Something which we said that to know an error, we have to add a redundant bit. So redundant bit is added, and we said we said something which was code word. So code, and we said, okay, the code word would be consisting of data. So I said message plus the redundant bits. So this was something which we did last time. Okay, and now we would use a Hamming code, which is used for forward error correction. Forward error correction. So it is not only able to, it does a error correction also. This is interesting. So first of all, we would see what was, if you remember the last slide, we said the it was by the mathematician Richard Hamming which developed this method, and it says that the redundant bits 2 raised to the power r should be greater than equal to message plus redundant bit plus 1. And now what we are doing it at the moment, we would do it for the ASCII code. And in the ASCII code, let's take another color. I say C. C in ASCII code is represented by 110011. So these are 7 bits. So our M is actually 7 bits. It consists of 7 bits. Okay, we have to see what should be the redundant bits for this. So I would ask your help to see what should be the redundant bits. So if I see 2 raised to the power r should be greater than equal to 7 n plus r plus 1. Let's take we say, will it help with redundant bits of 3? Will this above inequality holds? So I say 2 raised to the power 3, so that is 8. And what about the other thing? The other thing is 7 plus 3 plus 1. So this becomes 11. So 8 is not greater than equal to 11. So it means 3 bits redundancy will not work. Let's check it with R. Can you check it with 4? So let's say, so we check it for 4. Check with R is equal to 4. So we are saying now, so 2 raised to the power 4. So 2 raised to the power 4 is 16. And now again, we put in that formula, which was M plus R plus 1. So I just take other color. We had the formula which we had to compare M plus R plus 1, right? So your message was 7, and now we are saying 4 plus 1. So this becomes 12, and 16 is greater than 12. So it means our this is now hold this inequality. So it means for a message of 7 bits, you would need redundant bit 4 so that you are able to. So I hope it is clear to you. So it means for M is equal to 7, we would need 4 redundant bits. And that would help us that if at the error, there is an error, we would be able to see. Okay, so it means we will have a 4 redundant bits. Let me write that. For M is equal to 7, which is R should be 4. That's something which So let me just pause for a minute and ask you if it is all good at this moment. Are you able to understand? Is it good? Is it good till now? With Hamming code? This is an interesting thing. You would see the beauty of math. Yeah, okay. That's very interesting. So we have to see. So it means we have M, we knew M. What was the M? I again write. It corresponds to the C in the ASCII code. And we see this bit, this corresponds to the bit pattern, which was, let me see, 1, 1, and then 3 times 0 and 1, 1. So these are C. This is the ASCII code. So you are transmitting maybe with your keyboard C, you have to have 4 redundant bits, and this would help that at the receiver, maybe at Google, um, maybe at the server, it is able to see that if there is some mistake or some error. So we move to the next part. So it means we have 4 redundant bits. I write it. Now the problem is where we have to put these redundant bits. So naturally, should those redundant bits should be in the start of these 7 bits, at the end of 7 bits? That's the question. So the redundant bit would be redundant bit, which you have to put for error correction, redundant and detection. Redundant bits will be at locations corresponding to 2 raised to the power. Let's make n. So it means this would be the positions would be, the position would be 2 raised to the power 0, which is 1, 2 raised to the power 1, 2 raised to the power 2, then 2 raised to the power 2, which would be 4, and 2 raised to the power 3, which is 8. These are the extra bits which you have to put, right? So we have seen what C is. I would again write this C correspondingly. So once I put correspondingly, so I would just make 1 because that's a redundant bit. We do not know. Then we write at 2 because that is the second position, which is not, we are starting from the left side. Then we have 1. This 1 corresponds to actually this one, which is there. And then we have again 1. So this is 1, 2, 3, fourth position. Fourth position is a redundant bit. We'll leave that. Then we have 1, which is the second one. 1, 2, 3, 4, 5. The 6 is 0. 7 is 0, 3, 4, 5, 6, 7. Again, a bit which is there, which we have to find what is that bit. And then we have 1, 0 again, and then 11. So it means if we see how much total we have position bit now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have now 11 bits. And the 4 bits are redundant. We have to find, there is a process to find what would be these redundant bits which we have to put. That we will see. But at the moment, what we have seen is this is the 8th, this is the 4th, this is the second bit location, and I would put the redundant bits in red so that we are able to see. Okay, so this redundant bit, which I can say the first one, so we would find the first, and I would say check 1. Let's say check 1. So this is for, we have to find, is it a 0 or 1? It would be found on the basis of the values of the message, the bit values of the message. Okay, so we know at the moment, check 1, all where least significant bit is 1. What is meant by this? We have at the moment, we know, um, we can do like this. Sorry, if it is 1. So what I'm saying is we have now, for example, I would make it again, and let me move my header to somewhere else, and I would take, let me take some other color. Let's see if it gives me another color. Okay. Least significant bit. We know that how, for example, 0, 0, 0, 0 is 0. I quickly write 0, 1. This is 1. 0, 0, 1, 0 is 2. That is I'm writing with respect to the how we, just a minute. This corresponds to 2, 0, 0, 1, 1, that 3, 0, 1, 0, 0, that's 4, 0, 1, 0, 1 is 5, 0, 1, 1, 6, 7. And we say this is 8, 9, 10. I just leave it till 11. So this is something. And if you see where the least significant is 1. So if I see it is for position 1, yeah, it is for 3, 5, 7, 9. So we find that it is for 3, 5. So I just write where it is. So it is for, because we have to find for 1, the position. So we do not have this position. So we will start with the, so least significant bit is location. So we would say that it is for 3, 5, 7, 9, and 11. If you see the least significant bit is for 1 also, but we have to put the position of 1. So we leave that. So it is 3, 5, 7, 9, and 11. So we would take now from these above the values and put it there. Okay, what is the value at 3? 1, 2, 3, it is 1. So this is 1. And you have to take an exclusive OR. Then you would move to 5. 1, 2, 3, 4, 5, it is 1. Then exclusive OR 5. So 3. So we are starting from 1, 2, 3, 3, because 2 raised to the power 0 is 1. 3, 5, 7. So 3, 5, 6, 7. 7 is 0. Then exclusive OR of 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, which is 0. Then exclusive OR of 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is, so it means once we do this, you can see that 1, 1 is 0, 0 exclusive OR is 0, 0, 0 exclusive OR is 0, 0 exclusive OR is 1. So it means this thing we will have to transmit as 1. I hope it makes sense to you how I found. Then is check 2. We have to find what is check 2 at location 2. So here we will see all where not the LSB, rather the second bit is where second bit is 1. Second bit is 1. I hope you are able to see that quickly. Second bit is here because we are finding it for second. So second bit, so we would be seeing 3, then 6, then 7, then 10, then 11. So I write it again. So this corresponds to, and I write it in black. So this corresponds to 3, location 3. Let me write it location. So it corresponds to location 3, 6, 7, 10, and 11. We understand that. So we will have to make a quick. So what was at, I again see 3. 1, 2, 3. 3 is 1. Exclusive OR of 6. 1, 2, 3, 4, 5, 6, 0. Exclusive OR of 7. 1, 2, 3, 4, 5, 6, 7 is again 0. Exclusive OR of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1. exclusive OR of again 1, because that is the 11th position. So if we do this exclusive OR 1, 1, 1, 0, 0, and exclusive OR is 1. So it means it is 1. And then it means we would again put on this second position 1. I hope you are clear with this. If you have a confusion, let me know. So now we would move to the check 3. Check 3, or I would say check 4 rather. 1, 2, 3, 4. So again, we move to check 4. We have to see what should be what we would be transmitting here at 4th location. Again, here we would see all where the third LSB, third least significant bit is 0, the 1. So if I look at here, 3 is 4, 5, 6, 7. So it is actually location 4, 5, 6, and 7. I hope it makes clear to you. But the 4th position is itself. So we would not have a 4th position because we are finding for the 4th. So 5, 6, 7. So it would be something which I would do again with the black. We would find it that what is the 5th position? 5th is 1, 2, 3, 4, 5, 1, exclusive OR. 6 is 0, exclusive OR, and 7 is again 0. Yeah, so 1, 0, 0. So it means this is 1. So we will have to put it 1 here. I hope it's all making sense to you, and I would just make now the check. Now check 8, which is 1, 2, 3, 4, 5, 6, this one where we want to know what should be transmitted. And you see these parity bits or these redundant bits are dependent upon your message. We are calculating on the basis of your message. So in the 8, we would see the 4th list, 4th LSB should be 1. 4 LSB should be 1, is 1. So where is the 4th? It's 8, 9, 10th, and 11. And 8 because we have to find, so it means we are looking at 9th, 10th, and 11th position. And so it means we would find it like this. 9th. 9th is 0. So I again take black. 0 exclusive OR, because that was 9th, 10th, and 11th. Yeah. And the 10th is 11, 1, and again 1. So this is actually equal to 0 because that's the exclusive OR. So it means we would now put, and I again write. So this is our code. So I would write it again. So just to make it more clear. So for C, which was an ASCII C, M was, I write it, the M was actually 1, 1, 0, 0, 0, 1, 1. This was a C, which is ASCII. Message was this. But then we found out that we would send, and these are 7 bits, we would send the code word. Code word would be of 11 bits. And I just copy it from there just for which we have done, and I write it again in red. It becomes 1, 1, 1, 1, 1, 1, 2, 3, 4, 5 ones, then 1, 2, 3, 4 zeros, 4 zeros, and then 1. 1, 2, 3, 4 zeros and double 1. So these are now 11. So you send that. So instead of sending this code, which is here, you would be sending this code, which is redundant, which has 4 redundant bits. Why we are sending it? Because at the receiver, if there is some error, we should be able to see that there is some error, and we would see how it works. So let's go back and let's see that we have transmitted. So we have transmitted this code word to the receiver. I hope you are clear till this place. If you have any question, let me know. Otherwise, I would now move to the receiver. And what I do, I consider that there is an error. So at receiver, so let's make it at receiver, which may be at in some other place. And we see we receive, and we receive, and as I said, the Hamming code is able to detect and correct one single error. So we say we receive instead of this 1 1 1 1 1 0 0 0 1 0. So there is an error. There is 1 bit error. So receive instead of due to the maybe interference or due to any other reason has an error. Can somebody point out at which position the error is? You can type. Yeah. I think somebody has written something. I'm sorry, I'm not aware. Okay. Yeah. So at which position the error is? If you transmitted the code which I'm writing it on the, and you received at the receiver something. So at which position the error is there? The least significant bit or position 11 is error. Yeah, you can say that. It's the least significant bit or the one which is. So now this is something interesting. Receiver doesn't know that there is this zero is wrong. Now we would do an algorithm which, and then I would talk how the receiver would know that it has an error. So procedure, let me write the rule, or I would say the algorithm which checks at the receiver. Let's say I just write algorithm or the procedure through which it checks that it is how it's done. We put a C is a counter, and we put equal to 0. So you can code it, you can write a code on this. And then we would examine the positions at bit position that K is equal to, we know where we have to check 1, 2, 4, and 8. Why? These bit positions were the where we had put the redundant bits, the first bit, second bit, fourth bit, and eighth bit. And now we would check them. So we would see them again. If it had the correct parity, C remains 0. If there is some error, there is then we add 1 to C. And when all check bits are done, we see if C is 0, it means it is received correctly. If there is C is anything other than 0, we would say that bit location is the position of an error, and we would invert it because we know there is just 0 and 1, so there is one error. I would again say how we would check these bits per location. So we would check that. Yeah. So actually C is 0, and we would see first check 1. Check 1. On the basis of, now we would check on the basis of this received message. So the check 1 would be, we know these are the position 3, 5, 7, 9. I would just write it quickly because you know already 3, 5, 7, 9, 11, because these are where least significant bit is 1. Yeah. So we would see here, third is 1, exclusive or 5, 1, 2, 3, 4, 5, it's again 1. Then exclusive or of seventh position 1, 2, 3, 4, 5, 6, 7, which is 0. Then exclusive or of ninth position, ninth is again 0, and then of 11th, which is again 0. Yeah. Okay. Now we do that. So if we do 1 into 1 is 0, 0, 0, 0, 0, it is 0. Yeah. But what we had received it as 1, while we are our calculation is giving 0. So it means it's wrong. So it means wrong. So what we should do that? It means we would add 1 to C. So C becomes now 0 plus 1, which was, and it becomes 1. Now we would check the parity bit 2, check 2. Again, the same manner, you would check 2. Again, let me take black color. Now we would see check 2. And for, that was the second bit was 1, so it is correspond to 3, 6, 7, 9, not 9, sorry. It is 7, 10, and 11. So we would again do the same thing. We would see what is the third location. 1, 2, 3, 3 is 1. And then the sixth location, 1, 2, 3, 4, 5, 6, 0. 7 is again 0. And after 7, 10. 10 is 1. And 11 is again 0. Now we calculate it. So 1, 0 is 1, 1, 1 again, 1, 1, 0. So we get 0. So check 2 at the second position, it is 0. But we look at here, the second is 1. So it means it is also wrong. So it means the second position is wrong. So our C becomes, now C becomes 1 plus 2. Why 2? Because the second position is wrong. So we have this equal to 3. So this is 3. Now we would do quickly check 4. So again, I do that for check 4. And I hope you are getting it correctly with me. Check 4. Now we would check 4, and we had seen for check 4 we would do 5, 6, and 7 bit location because that correspond to the third bit, which is 1. So what is in the, I would say again, let me see that from, and let me zoom in. So now we have to check actually 5, 6, and 7. 1, 2, 3, 4, 5, 6. So it is, we have to see 5, 6, and 7. So the 5 is 1, 1, 2, 3, 4, 5. So 5 is 1, 6, and 7 is 0. Oh, sorry. So it is 0. Yeah. So this becomes 1. So check 4 has given us 1. And if you see 1, 2, 3, 4, it is 1. So it means this is correct. So we would not do anything. We would not do anything. So C remains 3. Now the last one, which is check 8. So we would see check 8. And for check 8, we know we have to check 9, 10, and 11 bits. So we would do that. And again, let me take that. 9 is 0, 10 is 1, and so it means 0 exclusive or 1 exclusive or 0, right? And now if you do that, it results 1. And in the 8th position, actually, you have 0 while you have this, so it means wrong. What we have to do now, we would add this location to the C. So I would take a red. Previously C was 3. So I would just, let me take a red pen. So previously C was 3. So we would 8 plus 8. And 8 plus 3 is 11. It means there is an error at bit number 11. So which was this bit, and error at position 11. We understand that. And if we know a bit error is there, we would just invert it. So once you would invert this bit error, which in the start somebody pointed out the least significant bit is wrong. So actually you would again correct the error. And it can correct single bit of error, and it could detect two consecutive error, detect not correct. So we are not going to go into the details how two consecutive errors are detected,